University in Turkey, Inspire Faculty Fellow, and is currently an assistant professor at IIT Indore. She has published many articles in reputed journals. She is also the first female lecturer of the series. Today's talk is, as you can see, observing black holes and understanding their imprints. I hope you all are excited about today's discussion and thank you for being here today. With that, I would like to request the head of SUNIT's Department of Physics, Dr. Divisha ma'am, to extend our gratitude and say a few words.
Thank you, Bhavya. So, greetings on the behalf of the department. I welcome Professor Manoneeta Chakraborty to this fourth talk of Sarabhai Online Series. Thank you so much, ma'am, for accepting our invitation and agreeing upon to talk on delivering observing black holes and understanding their imprints. The topic is very interesting as black holes is a mysterious object and definitely its imprint will help us to understand the physics of it. So by this lecture series, our eminent speakers are engaging more and more people on a greater level. So we have a great time having you all for sharing your valuable knowledge with us. So thank you so much, ma'am. And I congratulate the students. Even in this pandemic time, they are actively engaged in such activities. So thank you once again, one and all. Over to you, Bhavya.
Thank you, ma'am. Now I invite Manoneeta ma'am to please continue with the talk.
Thank you. First, I would like to thank you, all the organizers and Hate ma'am for giving me this opportunity to come here and interact with the students. And I would also like to appreciate the effort by the students to engage in this pandemic, like ma'am said, and interact about different areas in physics. Particularly, I am today very interested to talk about one of the things that I love working on is black holes. So today what I will be basically, trying to give you is a test of what actual black holes mean when we observe them, and how can we look at their observational signatures to even get a little bit idea about what are the physics going on. We have a lot of theories regarding black holes. They are one of the exotic, most enigmatic objects that you can think of. But in reality, when you actually do observe black holes, they often behave in certain ways that are still quite a mystery to us. And I would just talk a little bit about, how through observation, so you can get towards all these theories that propose to understand whatever the very exotic physics that goes on behind these enigmatic objects. So to start with, let's talk about what black holes are. So the black holes, like humans, come in many shapes and sizes. I will first start with talking about a class of black holes which are called stellar mass black holes, and they are basically the end state of stellar evolution. Later half of the talk, I will briefly mention what I mean by the other kinds of black holes. But for the stellar mass kind of black holes, it's very simple. They are very end states of evolution of the very massive stars. So as you know, just to give you the brief life history of a star, here is the star forming nebula, the gaseous region where stars start to form, the kind of stars we see in our sky, like the sun and so on. So they form in this kind of dense gaseous clouds. And some stars, which let's say are at least 20 times the mass of sun, after they are formed, follow this path as shown in this diagram. A typical sun-like star, which are relatively low mass, they follow the left path. But today we'll be concentrating only on this path. So these stars, which have masses more than 20 solar mass, 20 times the mass of a sun, after their normal life cycle, by normal life cycle, I mean when they fuse hydrogen and helium and other higher atomic number elements in their core to give away lots of luminosity. After they have finished this phase where they are fusing these elements in their core, and this massive stars go through this phase very, very quickly compared to a low mass star. So their lifespan is very small. They form a very, massive star, which is called a red giant. It's massive, not just massive, but its size is also very large, and its radius is very huge. And at this red supergiant phase, its luminosity increases many-fold times, though temperature is relatively lower. At this phase, all the nuclear burning has stopped, and some small nuclear burning is going on in the outer shells. And finally, when there is no more nuclear burning possible, the star kind of explodes in a very explosive high energetic event, which is known as supernovae. And finally, at the end, the core of the star remains at what we know as a black hole. So that's what we know as stellar mass black hole. And that's the formation history of a stellar mass black hole. So when we, if you ask a physicist what a black hole is, depending upon what type of physics he or she does, you will get up with a different answer. So the first question to ask is, what exactly is a black hole? How do we define a black hole? Obviously, as we describe the history of the black hole, the formation history of the black hole, it is synonymous to a complete collapse of a star. So basically it means that the gravity, the force of inward gravity, has completely won over any other outward forces. So there is nothing to balance the inward force of gravity, and it has collapsed completely. So this is basically what the rough framework of an introductory framework of a black hole. The typical parent star, as I told you, the normal original star, should have mass greater than 20 times the solar mass, and only then you will be able to form a black hole. Otherwise, you will end up with something called a neutron star or a white dwarf. We'll not focus on them right now. For now, let's focus on only black holes. So after the collapse has happened and the black hole has formed, the mass that remains from this greater than 20 solar mass star is roughly of the order of 4 to 20 times the solar mass. So the typical stellar mass black holes we see in our observations range from this range. Though again, I will question this, and we'll see that in recent times we have come up with very, very exciting discoveries, which has led us into some new domain which was previously unobserved or not unthought of, but unobserved. So if you ask a theoretician, they will come up with a definition of black hole where the core has collapsed and the center of the core has a singularity. A singularity basically means you have a zero radius and an infinite density. Now, any kind of singularity is kind of embarrassing for physicists. And what we would try to do is kind of, it's there, but let's avoid talking about it and let's come up with a practical solution the way we can talk about black holes. So the practical solution, the easier way to talk about a definition of a black hole, which we can relate to us in terms of observations, is in this manner. So in this case, black hole can be defined as an object where gravity is so strong that nothing, not even light, can escape its boundaries. It's black because light is also completely kind of absorbed in, quote unquote. And given that's the scenario, an easy definition would be it's an object whose radius is such that at that radius, the escape velocity equals to the speed of light. And that's a very simple, easy definition to come up with. So, by the way, this is the direct image of the black hole that was taken a couple of years before. And I will be showing this image many, many times. And I love it so much because I will soon show you that it has so much information in this not so resolved image that you would think. So much information that it's an amazing detection. And here you can see that some sort of a similar definition can be seen in this particular image. So given that what we have defined very crudely, very practically, with the simplest possible terms, let's write down what we can, define as the radius of a black hole. So as we know, this is very simplistic calculations, by the way. Obviously, there are more accurate derivations of the same, but surprisingly, this simplistic calculations works very well for the first principle results. So let's consider a mass m. Then we can write down the complete energy, as you know from basic classical mechanics, as minus g m by r, where r is the distance between these two objects, and half mv square. This is the kinetic energy, and this is the gravitational potential energy. So if you have to calculate the escape velocity, then you calculate the energy for which the mass becomes unbound, which means that E has to be greater than or equal to 0. So if we take the limiting condition, we can obtain the escape velocity formula, which probably a lot of you are very familiar with. So it comes down to 2gm by r. Now, as we have defined the black hole as an object for which escape velocity equals to the velocity of light, let's equate this. So once we equate this, V escape equals to C, we come up with a solution of R, which is the radius of the object. And this radius comes down to 2gm by c square. And this is a very famous radius. This, in very simplistic terms, defines the radius or the limit of a black hole, and it's called the Schwarzschild Radius, where the escape velocity becomes equals to the velocity of the light. Just to give you a numerical idea, for a black hole of 1 solar mass, this radius comes down to 3 kilometers. So imagine the entire mass of the sun squeezed into a radius of 3 kilometers. So which is even less than typical length of a city, typical radius of a city. So that means the density is super high. And there can be very exotic things happening in the neighborhood. So as we know, just following the general theory of relativity, that gravity can be more or less imagined as some sort of a very the dent that a ball makes when you place on the rubber sheet. This is the rubber sheet analogy. Again, this is just an analogy, nothing else. So here you can see an example. Here this is basically the space-time behaving like the rubber sheet. And if you place a black hole on this, it creates a dent, this kind of, which is kind of mimicking the gravity that you would expect. And because at the center of the black hole, there is a singularity, so eventually the curvature of the space-time at the center would correspond to a singularity. But we will not talk about that, because that's inside the event horizon, there is nothing we can observe. So we can very safely ignore what is going on inside and only talk about what happens outside the event horizon. So this is the event horizon, which is a radius, just the radius we just defined, at least in this case. Outside which we can observe things, but inside which light cannot escape, and it's not observable to us. Now, what happens is that because the density of the black hole is very high, it curves the space-time in this manner so that if there is any particle or light, even photon, coming close to the black hole, it gets trapped. It gets trapped in such a way that depending upon how far it is from the black hole, it can bend and then finally escape, or it can get trapped into an orbit and then start orbiting and eventually losing energy and thereby slowly crossing the event horizon. So here is most of the things that happens that we observe when we observe a black hole. There are a few other interesting properties associated with a black hole. They are not just, theoretically interesting, but also very important when we are observing any kind of radiation that is coming from these photons and particles that is coming from the surrounding medium around the black hole. And the signature of these effects are kind of imprinted on those radiation. The first thing that I will talk about is a very important thing, which is called the gravitational redshift. It basically means that because light is, passing through this gravitational veil of the black hole, the light waves take extra time and energy to climb out of the gravitational veil. And that results in a change of the energy and the frequency of the photon that is coming. So if you're observing the photon from a very, very far away distance, you will see the photon of our energy, let's say E or a frequency nu, to be very much redshifted. And the redshift can be calculated using this formula. So if a person is looking at, from a very far away distance, as the photon moves closer to the black hole, it will slowly go from blue to red. The other thing that is very, very important is time dilation. So as the photon or the particle moves close to the very close to the black hole or the event horizon, the time that passes in the apparently passes in the frame of the particle or the photon gets dilated and appears to move very slowly. So if you are observing a photon or a particle very close to the black hole, it will appear to take a very infinite time to cross the event horizon. A few more interesting thing is the effect of the light bending. It's a very, very funny thing. It basically means that the photon paths around the black hole is highly curved, and the light bends very much around the black hole given the gravity well of the black hole. And that basically means you can see light which is, from regions which are in principle obscured from your line of sight. So if you happen to hypothetically stand on the surface, close to the black hole, you can even see the back of your head. And that is also true for, anything else behind the black hole. For example, you may have seen these famous images many times. So here it basically means that this particular region whose counterpart was behind this particular black hole would be in principle unobservable, but because light bends so much, you can see this photons that are coming from the disk that is behind the black hole. So this effect of light bending can be very crucial when we are observing the emission from regions around the black hole. And finally, the tidal force effects are very important, particularly when we are observing, let's say, some star or any other black hole that is coming close by some other black hole. And it basically means with whatever object that comes very close to a particular black hole, of course, given a certain threshold distance, it gets completely ripped apart just by the simple tidal force effects. And, and it can be observed that, for example, a star, it was recently observed, which is very close to a black hole. It got completely ripped apart by the tidal forces of the black hole, and all the materials were then slowly inspiraled in and fell on crossing the event horizon of the black hole. And the last effect that is very, very important and very probably the most interesting is the rotation. I'll be coming back to that later. So we all know the Hair Theorem. It's a very, very helpful theorem, particularly when we are talking about understanding and modeling the physics of black holes. It basically says that unlike any other objects, other sun, stars, moon, planets, whatever we see, where the properties depend upon a bunch of physical parameters like temperature, age, composition, luminosity, black holes have this very unique property that their entire physics can be completely, defined by only three parameters: their mass, their angular momentum, and their charge. So that basically means that observationally, if you are able to measure at least three of these parameters, then you will be able to more or less very accurately explain the physics and apply the existing theoretical models to your observation. So one of the major objectives when we do observations of black holes is to estimate these three properties, particularly the first two, the mass and the angular momentum. So what happens when a test particle or a photon approaches a black hole? So at very, very far away distance, it basically, it's not that crucially different from any other object having the same mass, because the distance is very, very far away. But as you come closer and closer to the event horizon, then it gets slowly attracted by the gravitational field of the black hole, and it starts inspiraling or rotating around the black hole to conserve the angular momentum. This is something you would have expected for any other normal object as well. But the most interesting thing happens when it comes very close to the Schwarzschild radius that we had just defined. So around close to, 3 Schwarzschild radii, some interesting effects starts to be observable, like various effects of the gravitational curvature of the space-time made by the black hole. And as it reaches the 3 times the Schwarzschild radii, the particle cannot remain in a stable circular orbit, and it falls very, quickly in a spiral on towards the event horizon, and the material gets quickly sucked in. At around 1.5 times the Schwarzschild radius, the photon also get trapped, not just the matter particles. The photons are also getting trapped at this radius, and they kind of move in very closed circular orbits and slowly go into shorter and shorter circular orbits. And this is basically what was observed in this is called the photon sphere, and this is basically what was observed in the first image of the black hole. And finally, when it reaches the event horizon, it gets completely dark, and the particle and the photon is lost forever, and there is no history that you can extract out of the sucked in particle or the photon. By the way, here the event horizon is somewhere even at a very shorter radii. This is just some larger radii where no stable orbits of the photons or the particles can even be possible. Okay. The last thing regarding the black hole properties, what I would like to talk about is the rotation, the angular momentum. The angular momentum can have amazing effects on the kind of emission that we receive from around the black holes. And surprisingly, what we see that most of the black holes that we observe in our sky, they are rotating with extremely high spin values, and often what we call maximally rotating, meaning their spin is very close to the maximum possible spin that is allowable for the black hole. And here you can see such example of a non-rotating and a rotating black hole. The next thing that happens for a rotating black hole is the definitions or the positions of the event horizon and the innermost orbit of the photon and the particle that is possible changes. So for a properly rotating black hole, and if the spin is very high, the event horizon can be, the event horizon can be even smaller, much smaller than the RS that we have calculated, and the age of the disk, age of this orbit, that where a stable orbit is possible, that radius becomes also very smaller, which basically means in principle you can probe much closer to the singularity, or the the center of the gravitational well of the black hole. So certain effects are much pronounced for rotating black holes. And not just that, when the black hole is rotating, it's also kind of the rotation affects the curvature of the space-time as well. So basically, it not only curves, not only puts a dent, but it kind of drags. So the space-time becomes kind of dragged and sheared as the black hole has a high spin. And those effects can lead to some very interesting observations, which I will talk about. So the next question to ask, good, these are all very interesting properties, but black holes are black. So where can we look for them? How to look for them, particularly for the stellar mass black holes? So the answer is, to look for them, what we immediately do is obviously look for the effects of gravity on their surroundings. And the best place for this is the systems where the black hole is in a binary orbit with another star, because then it can very easily kind of attract matter from the star, and the matter will get heated up, emit a lot. We can observe this emission from the heated up matter, and whatever the gravitational signatures that we have just discussed will be imprinted upon this material and the emission that is coming from the heated up material. So these kind of systems are very bright in X-rays. Why? Because, okay, I will explain why. But physically, the reason is because this matter is getting attracted by the strong gravitational potential of the black hole. Here, it gets heated up very much. And as it gets heated up, the temperature can reach up to even 10 to the power 7 K. So, okay, which is a very huge temperature. And if you look at this 10 to the power 7 K, the corresponding frequency falls bang on in the X-ray wavelength band. So this kind of systems are most bright in X-rays. So if you are, if you want to look for black holes, the systems to look for is binaries, and the telescope to use is X-ray telescope. So what we look for is some systems which are very bright in X-rays, have a bright star, thus that has an apparent motion which is synonymous to the motion it would have when it's moving around an unseen object that would have a mass comparable to the mass that you expect of a black hole. So these are very bright, and also very variable X-ray sources, and their luminosity can be so high that certain black hole systems, such binary systems, are the second most luminous X-ray object in our sky. What is the first most X-ray luminous object in our sky?
Pulsars.
What was the second answer?
Supernova.
Supernova.
Okay. When I mean in our sky,
Quasars.
Sun.
yes, that's the correct answer. Sun. Because what I mean is not just the intrinsic luminosity, but how it appears to us. And since the sun is the brightest object closest to us, across all wavelengths, and it's very close to us, sun is basically brightest in almost all wavelengths, including X-rays. But the black hole binaries, X-ray binaries, are the second most luminous objects, and they can give huge copious amounts of X-ray luminosity. And that can lead to various interesting observations and inferences. Okay, so why are they so X-ray bright? How X-ray bright they can be? To answer this question, the estimate, small back of the envelope calculation that we can do is, let's assume a hydrogen atom. And let's assume that it's falling from infinity to the Schwarzschild radius of the black hole. If that is the case, what is the total amount of energy that it will lose? Coming from infinity to the gravitational potential and close to the Schwarzschild radii. So if we calculate that, it is just given by GMM by RS, where RS is the Schwarzschild radii. And for a typical black hole, this comes out to be a huge number, 0.1 times the rest mass energy of a proton, which is a huge number. It's 10 to the power 20 arcs per unit gram. So accretion, this process of the black hole accreting matter and slowly falling on to the event horizon, and in the process this getting heated up, this is called the accretion. And accretion thus becomes the most efficient process of energy generation in the X-ray band. And it can be thus the X-ray binaries that contains a black hole and a companion star can be the most X-ray contributing objects in the entire cosmos. So here you can see that a typical diagram of a X-ray binary, the various components. There is a black hole, there is a main sequence star, the black hole's gravitational potential makes sure that it starts attracting matter from the companion star, but the matter that it's attracting has an angular momentum, so it doesn't fall directly. It slowly inspirals, thereby forming a disk. The disk is extremely hot because of the accretion process and the corresponding gravitational potential energy, and it radiates a lot of luminosity and X-rays. And associated with that, there are often very strong jets and winds also present. And often when we talk about observation of black holes and observational imprints, what we talk about is the radiation that is coming from this this block. So I just said that astrophysical accretion is one of the most efficient sources of energy generation. How can I substantiate that statement? So we can do a quick calculation again between the amount of gravitational potential energy that is released when an object moves from, let's say, a unit mass moves from infinity to the Schwarzschild radius of a black hole, and the amount of energy that is generated per unit mass in a nuclear fusion. So if you calculate these two, the energy generation through these processes, you will see that the energy generated through nuclear fusion, which is we know as one of the most efficient energy generation processes, it's about 0.007 times the rest mass energy of a proton, whereas the accretion onto a black hole will give you around 0.1, which is just calculated. So that means it can be the many times more efficient energy generation mechanism compared to a nuclear fusion. And if we just calculate the luminosity from here and equate it using this very famous black body radiation formula or the Stefan Boltzmann formula, we can get an idea about the temperature of the region from where this particular radiation is coming. And we can see that the disk temperature has to be about 10 to the power 7 K, which falls in the X-ray wavelength band. Also, why are black holes worth probing and worth studying? Of course, they are exotic, but it's more important than that. There is more to it than that. Firstly, what happens around a black hole is the gravitational field reaches the strongest form that is possible, meaning gravity in general is a very weak force. So we know, the theory of gravity is given by Albert Einstein, and it's called the general theory of relativity, and it works very well. But there are many alternate theories of gravity as well, which can do quite well compared to GR in most cases. So the question is that which theory of gravity is the most favored one, or the most accurate one? And we need to test between these various theories of gravity. The problem is that gravity being a very weak force, in most cases, the difference between the predictions of this model is so small that observationally it becomes impossible to differentiate between the different inferences or different estimates. But around object like black hole, because gravity enters the strongest field regime, all these models becomes non-degenerate. And you can actually, test whether GR was indeed correct, if the different predictions of GR, the general theory of relativity holds true or not, and test the alternate theories as well. Of course, it's the end state of stellar evolution. Okay, before that, I should show you this very interesting plot. This plot basically shows you the gravitational potential in the x-axis and the curvature, which basically, the curvature which basically parameterizes the strength of the gravity around an object on the y-axis. So the more this particular quantity, the better, the stronger is the effect of the gravity around it. And here you can see the several objects are shown in this plot. Here you have all the stars of the Milky Way, various solar system objects, various other normal kind of stars. MS means the normal stars. And the interesting thing to note here is all the big objects like the supermassive black holes, the supermassive, the galaxies containing the supermassive black holes like AGN, and all the other stars in the Milky Way falls much lower in this diagram, whereas the XRBs are the stellar black holes that I am talking about in the binary systems. XRB is extra binary. Occupies the topmost region of this diagram, meaning the strength of gravity is the maximum closer to the stellar mass black hole systems. And if we can probe close to these objects, we can, test around among various theories of gravity and, test their accuracy to unprecedented levels. Also, these black holes are the end states of stellar evolution. We would always like to know, how the stellar evolution history evolved across the history of the cosmos, and that. In that sense, we will also like to know about how black hole formation and evolution took place, because one of the questions we would like to ask is, let's say we have the stellar mass black holes, which are of the order of, let's say, 4 to 20 solar masses. And we have the black holes that are at the center of the galaxies, which are about 1 billion to million to billion solar masses. So how do one bridges these two? Where are the missing links? Why is there such a huge gap in the mass of the two black hole populations, starting from 10 solar mass to 10 to the power 6 solar mass? So one would like to answer these questions, that where do the black holes that are in the center of the universe, the center of the galaxy, come from, and how do this stellar mass black holes grow? Because remember, as they are eating up mass or eating up matter, they are growing. So how do their evolution changes with time? And finally, how much effect such this evolution and the different black hole interactions have on the process of galaxy evolution? So these are the questions that we are trying to answer as we are studying black holes. And for that, observationally, what we are trying to do is look at black holes in such extra-binary systems. But interestingly enough, though they are the most prominent in X-rays, they actually emit all across the wavelength band, and different parts of this system emit in different section of the wavelength band. For example, the black holes often show strong jets, which are bright in radio. They often show, various the outer edges of the disk are often luminous in optical. Some base of the jet is luminous in UV and optical, and so on and so forth. So, in order to completely understand the various workings of different parts of this X-ray binary system and different areas where the black hole is living, it imprints, only broadband studies, where we are looking at a large part of the wavelength spectrum, can help us and reveal the dynamics and the origin of the several components in our emission spectrum. And that's what we need to do. And the second thing is, very crucial thing is, most of these black hole X-ray binary systems are very, very variable in their luminosity. So here you can see how it is. So here you can see the luminosity that is coming in the X-ray range in this 15 to 50 keV wavelength range with time. On the x-axis we have days, and on the y-axis we have photon counts per second. So as you can see, the photon intensity that is coming from this particular system is changing hugely over different days. And not only that, that change, the way it's changing is different between different wavelength bands. So that means the emission, first of all, is very highly variable. So that means all these components are completely changing. They are dancing, basically, in other words. And that are very, very interesting, because the dancing is often related to the geometry of the space-time of the black hole. And finally, the variability is strongly dependent on energy. So this is not only true for, by the way, this is not only true for stellar mass black holes, but this is true for the supermassive black holes as well. So often I will go back and forth between the stellar black holes and supermassive black holes, and I will show you that a large fraction of the properties of the two actually are same. Only what you have to do is you have to scale the property for the masses. So here you see the very famous image of the black hole, the direct imaging of the black hole that was taken by EHT. But the thing to note here is that the image is not a one single image, but a bunch of images was taken over several days. And if you cleverly look at this different images over the different days, you will see that this intensity pattern is changing. And this is exactly changing according to what you expect from the photon sphere around a black hole. So that means that the intensity is variable, it's dependent upon energy, and it's over a large wavelength range. So basically, in other words, what we need to go forward is broadband, large wavelength range, simultaneous high resolution observations that will be able to distinguish this dancing of the black holes. So to do that, I will give you some examples of the kind of features we do study and what kind of information that they can give. So the first thing to look for is the spectral emission that we see from the black hole X-ray binaries. So spectral emission means how the photons varies as a function of energy. So here you can see a cross section of a typical black hole X-ray binary system. The black hole is sitting here, and this is what you see is the accretion disk. And around the accretion disk, there is a hot region, which is basically a plasma, meaning a hot region of charged particles, which are not at thermal equilibrium. So when you look at the photons that are coming from this entire system, there are different components that are contributing to that. First, you have the thermal emission. This is, if you are familiar with, this is mostly a kind of a black body radiation that is coming from the disk. This is the accretion disk. So the accretion disk is quite dense, which basically means all the particles in that disk are basically at thermal equilibrium. And as they are thermal equilibrium, they give rise to a kind of a Planck kind of a function, black body radiation. You can assign a temperature to different regions of the accretion disk. And they typically peak at, one of the lower energies. And once you have the different photons coming from this thermal accretion disk, these photons go in all possible directions. And as they go in all possible directions, some part of them go into this hot plasma. This hot plasma is often called the corona. And as it goes into the coronal region, what it does is it interacts with the different charged particles that are present there. And it undergoes some sort of a inverse Comptonization or a Comptonization process, where the photon interacts with the charged particles. And that results in a non-thermal emission, where the particles are not at thermal equilibrium. The emission cannot be assigned a temperature, but it's pumped up to higher energy. So the entire, the spectrum, final spectrum that you see is a combination of the thermal emission from the disk at the lower energies and non-thermal emission from the corona at the higher energies. Okay. And this variation of the spectrum also changes as the disk moves back and forth. The disk is not always steady. It moves back and forth depending on the efficiency rate at which the black hole is kind of eating up matter from its companion. So the disk is highly variable, and depending upon that, the spectrum can look like this, or it can look like this. In this case, the emission in the case of the black one, the emission from the disk is dominating. And in the case of the red one, the emission from the coronal region is dominating. And by carefully modeling this particular spectra, because it's coming from the disk and the coronal region, you can get a good estimate on the age, the radius of the disk, and from that radius, you can get the idea of the innermost radius, stable circular orbit radius, and that can give you estimate on the black hole mass and spin, which is two of the three parameters of the black hole. So that's one way. The other interesting feature that is very, very exciting for us observers is something called the quasi-periodic oscillation. In this case, what we do is basically look at these variabilities that are coming from the black hole and go to the Fourier spectrum or the power spectrum of it. So how periodic these variabilities are. And what we see is in the power spectrum, it shows how variable as a function of the frequency. And in certain cases, what we see is there are some peaks which are not completely periodic. A complete periodic will mean that there will be a very narrow line. This is not super narrow. There is some sort of a width to it. So that's why it's not periodic. It's quasi-periodic. This is basically the power spectrum. And at certain frequencies, you will see the quasi-periodic nature of coming from this black hole X-ray binaries. And these are very, very exciting. This quasi-periodic oscillation shows a wide range. They start from millihertz frequency ranges to kilohertz frequency ranges. And they have information about different sites that are very close to the event horizon. They can be present at the very high frequencies like shown here, around 200 to 500 hertz in this case, but around few hundred hertz. And basically, the high frequencies QPOs are supposed to originate from close to the innermost stable circular orbit, meaning the minimum radius orbit that is possible. So what happens is that the innermost orbit that is possible, that is very close to the event horizon, and there sometimes due to the effect of the gravity, because you're being very close to the event horizon, some sort of a disturbance develops, which results in a blob of matter developing around near that particular radius. And this blob is in this particular orbit, and the orbit is rotating, right? The matter is rotating. And as they are rotating, you can calculate the Keplerian frequency by equating the the angular momentum with the corresponding the centrifugal force with the corresponding gravitational force, and that will give you the Keplerian orbital frequency. And if you calculate that orbital frequency, it will come out to around few hundred hertz for a typical black hole around the ISCO orbit. The ISCO is, as I said, given by 3 times the Schwarzschild radius, or 6 gm by c square. And from there, we can, if we measure the QPO and we measure the frequency and we put down the frequency here, then we will get the R ISCO. The R ISCO can be written as 6 gm by c square. So thereby, we'll get the mass of the black hole. So this is another way to get the mass of the black hole. Not only the mass, it can give you an idea of how the hydrodynamical matter near close to the event horizon behaves when it's in the disk close to the inner edges of the disk. Often twin QPOs are seen instead of one, and they are generated by some sort of a disturbed orbit. There is an orbit, but the orbit it is disturbed. The disturbance gives the second frequency. In low frequency also, QPOs can be observed like this. And here you can see the QPO that is observed in another power spectrum is roughly around few millihertz, 50 millihertz. And such low frequency QPOs are explained using the very interesting idea of the frame dragging effect. So what does a frame dragging effect tell you about? It basically means that as the black hole is sitting there and spinning, as I told you, it's dragging the corresponding curved space-time. It's making a kind of a shear and resulting in a bunch of vibrations around the dragged space-time, and it results in some sort of a this kind of effect, like a top precesses like this. So this kind of effect happens due to this spinning effect of the black hole, and this is called relativistic frame dragging. In principle, this is true for any spinning gravitating object. Even Earth shows this. But obviously, it has much smaller, scales compared to a black hole. And this effect is a very strong general relativistic effect. And it results in this wobbling of the spacetime. Here you can see an example. And, here you can see that very close to the black hole, the innermost regions of the accretion disk is, wobbling as this changes, and the frequency of this wobbling is called is manifested as the low frequency QPOs, which are shown here. These are driven by the black hole spin and can also help you very helpfully to measure the spin of the black hole. So what are the advantages of the QPO? They have been explained using a bunch of models, and there are a lot of uncertainty in getting to the mass and the spin parameters, starting from what we see as the properties of the QPOs from this power spectrum. So the advantages are they can be very helpful in constraining the neutron star parameters, can give you the mass, then the spin. This lens theory precision that I just talked about is a very direct corollary of general theory of relativity, and it can give you a laboratory to test the GR effects. Therefore, also there is an effect of magnetic field that helps triggering these blobs and QPOs, and it can give you a possible estimate on the effect on the magnitude of the magnetic field that is passing through the accretion disk and associated with any kind of black holes. And magnetic field can be very, very important for understanding the properties of black holes in inner regions of the accretion disk, and when we are talking about jets later on. And also, there are some challenges associated to QPOs. For example, when we say that the blob is forming at certain regions close to the ISCO, that may not be exactly ISCO. So there are some variations on the source parameters, for different sources, because depending upon how far it is compared to the innermost orbit. Till now, there is no such theoretical model that can address all observed characteristics of the QPOs and their evolution and across all frequencies. So that's a huge problem. But that makes it so much more interesting, because that means that we still don't understand the complete physics that is going on around black holes. And there are a lot more to do. And finally, there is a lot of, I haven't talked a lot about neutron stars, but neutron stars are also very dense sources like black holes, but they are not black. But they also show QPOs and have some similar effects on the surroundings. So you would expect some sort of a, translation from the kind of things we see in black holes to the kind of things we see in the case of neutron stars. But observationally, we see that there is quite an significant difference than we expect, and that has resulted in challenge to our understanding. And finally, not finally, but last but one thing that I want to say is observational thing is spectral lines. I have talked about the photon emission that is coming from the disk. I have talked about the, the photon that is interacting with the corona. So this is called the continuum emission. But apart from that, another thing happens. Yeah. Is there something? Okay. I will try to wrap up within 5-10 minutes. Is that okay? 5 minutes more?
Yes, no problem. You can take your time.
Sorry about the delay. Okay, so one of the last thing I want to talk about is, this line emissions. So the spectrum that we observe from a black hole, it's not just a continuum spectra, but there are this, very narrow lines which come from absorption and emission of photons from this various atoms and ions that are present in the disk. This line energies correspond to the various transitions of those elements that are present in the disk. So this lines can be a very important, again, signature to get an estimate on the black hole physics. So not only the black hole have the continuum emission, but as the photons are getting emitted from this hot plasma and this disk, these photons are heating the disk, and these photons which have a long high energy, they hit the disk which is dense and at a cooler temperature. And as they hit the disk, cool dense disk, the photons corresponding to the various transitions get absorbed, and a reflected part, and the part is reflected, which gets the imprint of the absorption lines. Here you can see that theoretically how such absorption line will typically look. This is absorption line, so it will be inverted, but just for our benefit, I have kind of inverted it and shown it like this. So this is the reflected absorption line, and it has a particular characteristic feature or a characteristic profile like this. Why does this happen? This happens due to a combination of a number of effects. First, what you have is you have the disk. Now the disk has angular momentum. A part of the disk is moving. If you are looking from this side towards the black hole, a part of the disk is moving away from you, and a part of the disk is moving towards you. The part is moving towards you is blue shifted, and the part is moving away from you, it's red shifted. Oops, sorry. So you get a horn-like profile for the red shift and for the blue shift. As you imagine a radius somewhere here, which is giving a rise to the absorption line. Then you have the special relativistic effects, which basically tells the photons that are coming from the regions that are moving towards you are kind of boosted up due to special theory of relativity. So the blue shifted, I'm so sorry, the blue shifted part of the line will get, boosted up, and the other one will get diminished. Then you have the general relativistic redshift. Remember, we talked about redshift in one of the earlier slides, which will shift the entire spectrum towards the lower energy values or lower frequency values. And then you get the radiation from many such orbits, not only one single one. So that means you will get many such peaked horn profiles, and eventually you get some sort of a skewed line like this. And that will have all the effects of all this very interesting effects or physical processes. Okay, once we have that, then the next important thing is, because the line profile depends on which radius it's coming from, if the innermost edges of the accretion disk is contributing to the line profile, then it matters whether the black hole is rotating or not. Because if it's rotating, the inner edge of the disk is very far away, and you get a profile like this. Whereas if it's not rotating, if it's rotating, the inner edge of the disk is much shorter, much closer, and you get a much more elongated profile. So just by looking at the line profile, you can get an idea of the ISCO, and you can get an idea of the spin and the mass of the black hole. Here you can see another example of rotating and non-rotating cases. This is another real-life example of a very famous black hole called Cygnus X1. And using X-ray data, this is how it looks like. This particular black hole has a significant rotation, so you see there's this very skewed line that is typically observed. Okay. And last thing I would like to say is one of the last features I would like to say is the jets. I told you some of the black hole give up very strong radio jets that is perpendicular to the disk plane. They are like this. So this is the black hole, you have the disk, this is the companion star, and often there are very strong radio jets that is given perpendicular direction. In some cases, the disk lobes are very bright in radio and can be resolved. So here you can see there is a disk lobe emitted from a black hole somewhere sitting here, and as it moves forward, it's kind of gets wider and wider and separated. And sometimes apparently the jets are observed to show a superluminal motion, meaning it seems to move at a speed higher than the speed of light. Obviously, it's a projection effect. It cannot move at a higher than the speed of light, but it basically means the jets have velocities which are very, very close to the speed of light. They are very prominent in radio, and these are hypothesized to be powered by the angular momentum of the black hole in presence of a magnetic field. So the black hole is spinning, and that is dragging on the corresponding, space-time and matter on the space-time, and the matter has magnetic fields passing through it, and this magnetic fields gets twisted and turned as the frame gets dragged, and this twisted and turns magnetic field then get released. The energy of this angular momentum gets released through this magnetic field in the form of jets in a different way, perpendicular to the accretion disk. So here you can see artist impression where you see the jets. The jets can be full of photons. They can have significant amount of particles as well, depending upon whatever the strength of the launching was. And right now, one of the key mechanisms, there is still a lot of ambiguity in how the jets are launched, but one of the key mechanisms that is used to explain the jets is called the Blandford-Zanuck mechanism. And it basically says that, just by using the angular momentum and simple electromagnetic mechanism, one can actually extract the spin energy of the black hole in form of the jet launching. And of course, the magnetic field has to be present. They are very luminous in radio wavelength band, And often what we see is that there is a correlation between, a very strong correlation between the amount of jet that you are launching and the amount of material that is present in the disk. So it kinds of a, energy budget. If the disk is behaving in a particular specific way, then only the jet gets to launched. Interestingly enough, such black hole jets are not only just seen for stellar mass black holes, but they are seen for supermassive black holes as well. Actually, they are seen even more prominently for supermassive black holes. And you can see very, very nice few kiloparsec scale jets with lots of features. But such jets are also there for stellar mass black holes as well. And here you can see for the supermassive cases, for a particular galaxy, which has a black hole at its center, it's launching very strong jets. And these are the lobes of the jet. The jets are so large, I mean, it can cover a few kiloparsec and go to, such large scales. And as it passes through the interstellar medium, it interacts with the existing particles and ions, and that can give rise to this very nice lobes, which are very bright in radio. There can be other kind of jets as well, where the lobes are not so bright, but the jet centers are very bright. But these are for the supermassive black holes, and they are also very, very interesting to study, because in this case the jets can be resolved. But curiously enough, a lot of properties of the jets are almost similar to the properties that you see for stellar mass black holes. Just the parameters should be scaled for the mass, because supermassive black holes have few billions of solar masses. There are still existing lots of questions regarding the black hole jets. Firstly, how strongly the jets are related to the black hole speed. I just told you the angular momentum is the main reason for launching of the jets. But observationally, there is a lot of still doubt as to, whether the most spinning black holes are the ones giving rise to the most prominent jets. Secondly, as I said, depending upon accretion, at different states, jets are launched, and in certain cases, jets are quenched. So we have to really figure out how the physics of what is the magnetic field going on in our accretion disk regions that is giving rise to this particular jets. And how do they evolve as they travel, away from the black hole, the central engine, often what we call. And how the corresponding magnetic field inside the jets changes, giving rise to various features in the jets, as you can see. So there are lots of questions regarding jets, and here you can see the jet luminosity, the radio brightness of the jet is very strongly related to the X-ray luminosity, the luminosity of the disk. So these are the different black holes that are plotted on this. And for these different black holes, the luminosity of the disk is very strongly related to the luminosity of the jet. So there is a strong correlation, but still there is a very much uncertainty, because the disk luminosity is also varying, and at what particular luminosity will the jet significantly launch, and what particular state of the accretion it will get suppressed. That is still a huge amount of a particular area of a huge amount of debate. And what is the role of magnetic field in this entire picture? Okay, so I'm completely out of time, so I will stop. I would like to stop here, but I can take questions.
Thank you so much, ma'am, for talking so passionately about black holes and the physics around them. The way you illustrated different concepts and explained them in such a clear way was amazing. So now, if participants have any queries or doubts, I encourage them to share them in the chat box. Until then, ma'am, there are a few questions.
Sure.
Gaurav asks, if there is dark in between the black hole, then how is suspected suspected that the internal of the black hole is rotating, or still how do we know and by what observation we can get knowledge of rotating or non-rotating?
Very good question. So I think I have a little bit answered that in the later part of the talk. I have told you that the various observational features like the line emission or like the QPOs, which have direct imprints of the rotation of the black hole. So the rotation basically, drags the space-time that is around the black hole. So this frame dragging effects results in, let's say, the wobbling precessional frequencies, or even the change in the innermost orbit that is possible, and that modulates the profile of the line. So just by looking at these features and then inferring that what is the possible spin that is, should be there to give this particular frequency of the QPO or this particular profile of the line, we can estimate a spin. And in this case, often we see the spin we estimate is quite large enough, and most of these black holes are very rapidly rotating. Observed black holes.
And he continues, and what is exactly rotating if we are able to suspect in between the dark region, as there is nothing, just gravity? And he again continues, and why light, an electromagnetic wave, bends towards gravitational field of the black holes, as it shows a relation between electromagnetic phenomena and a gravitational one. And then again, but why? But why is this?
Okay, let me take the first question first. What is exactly rotating if we are able to... So rotating basically means that whatever the central object that is sitting there has an angular momentum. And if you think about it, it has to have an angular momentum, because the original star from which it collapsed, that original star had a significant angular momentum. And when it collapsed, the core of the star had also a significant fraction of that angular momentum of the parent star. And when this core had collapsed, it has resulted in a smaller radii. But if you have to conserve, angular momentum, the angular momentum will still be conserved, and it will result in a relatively higher, spin. So that's basically meant by, rotating. We cannot actually see something actually, the way we see a ball rotating, but it basically means it has an angular momentum. And the way we quote unquote see it is basically its effect on the surroundings, like most things with black holes. Like we see effects of gravitational field on the surroundings. Similarly, we see the effect of the angular momentum also on the surroundings, and we see the frame gets dragged. It's not same as a non-rotating black hole sitting there. The second question is why light and electromagnetic wave bends towards the gravitational field. It's just because light is also something very much similar to how a particle will behave, something just with a mass 0. So in this mass 0 and velocity c, the velocity of light. So in this case, of course, you can calculate what the path will be as it passes through the gravitational well of the black hole. Remember that when the black hole is sitting on the quote-unquote rubber sheet that we are thinking of, which is basically our space-time, it's basically creating a curvature, and there are certain, given that there is no other force, the light, if you place it on the space-time, it has to follow a certain path. Much like when you solve, Newton's laws of motion, that has also give you a certain trajectory, right? So if you give in general relativity, there is some equivalent of Newtonian law of motion, and if you put down the curvature of the black hole, or the curvature of the space-time, sorry, not the black hole, but curvature of the space-time due to the black hole, it will give you an equation of the trajectory, or result, a formula of the trajectory of the particle or the light. And that trajectory shows that it has to bend, given that the space-time has got curved. I think that's the question. I don't understand the last part of the question in relation to the electromagnetic phenomenon and the gravitational one. I don't exactly get that, but I I can say that, because the photon has to follow a different path, the corresponding emission obviously has to depend on that, the changed, the modified path that it has to follow. Okay.
Siddharth asks, the black hole jets remind us a bit of pulsars. So how can these be used as standard candles?
I didn't say black hole jets are used as standard candles. In fact, most jets cannot be used as standard candles because they are extremely variable. Standard candle means, something quite stable, something that is bright, something that is, you know exactly how its luminosity is, and its exactly its luminosity varies. You wouldn't like it to change that much. But for most black holes, the jets are highly variable, which basically means they cannot be used as standard candles. But yeah, it looks a little bit like pulsars, but however, the physics is slightly different. For the case of pulsars, the main reason for the jet is a magnetic field. There you have a very ultra strong magnetic field, which have this magnetic lines of forces that guides the charged particles along the magnetic lines of forces, and that results in the very strong coherent radiation that you get from the pulsars. But in the case of black holes, as I just said, that it's the angular momentum. So it's more related to the disk and whatever is going on in the inner edges of the disk related to the frame dragging and the differential rotation effect. So the jet launching physics is very different from pulsars to black holes, though they may look a little bit similar.
Aditya asks, is the accretion disk formed in the plane perpendicular to the axis of rotation of black hole, or is it formed in any plane?
That's a very exciting, interesting question. So the answer to the question is, in general, it forms in the plane of the plane perpendicular to the rotation of the black hole, because that is the most optimized orientation in terms of the angular momentum. But there have been some scenarios where the disk was disturbed, and due to the disturbance on the disk by, say, some external object, it may be another passing star or a passing black hole, something like that, the disk can get disoriented and in some different angle. If that happens, there have been a few cases like that observed, but if that happens, that is not the most favorable condition. And in that case, what these two things will walk, the black hole angular momentum and the angular momentum of the disk will walk in tandem to bring it back to the original situation. So over time, it will try to go to, again, a perpendicular to the angular momentum axis scenario. Yeah.
Harshini asks, according to the no-hair theorem, charge is one of the properties associated with the black hole. How does one go about determining this charge?
Yes, that's a very good question. And that's the answer is, right now there is actually not a very good way of determining this charge, because it's such a very difficult quantity and abstract quantity. It can be observationally very difficult to measure this charge. Right now, the answer is we are really don't have a very good handle on measurement of this charge. However, as the observational, I didn't get much time to talk about the observational facilities, but over time we have been improving the observational facilities. And as we are improving the observational facilities and coming up with much improved sophisticated telescopes, we can go to much higher sensitivities. And there have been some theoretical models and estimates which says that if we can measure at higher sensitivities, there are some properties of the black holes, like some precisional frequencies and other things, that can have a dependency on charge. And that dependency can be measured with those improved sensitivities. But this is something we have to do. Not yet done.
Shyam posted, at space-time singularity, Einstein's general theory of relativity would have broken down. Why and how?
It's not necessarily broken down. I mean, there is nothing that, well, broken down is such a strong word, which basically means it will contradict. There is nothing it contradicts, but any kind of singularity, is uncomfortable, because singularity means any kind a physical parameter that we are dealing with, like densities, like pressure, they become infinite. And how do you deal with infinity? This is such a awkward awkward thing to deal with. It doesn't have to be general theory of relativity. It can be any other theory of gravity. But wherever you have the singularity, that is a thing that makes physicists uncomfortable, because that means something becomes infinite, which is very hard to even contemplate, right? Visualize. But for observational perspective, as I said, we tend to stay outside the event horizon and be happy with that, because we don't know what's going on inside. So there is a singularity, there might be something outside the singularity. As long as we are outside there and we are observing, we are good to go. It's a little bit of cheating, but fine.
Disha asks, can you tell us about Hawking radiation, which seems to be a paradox from the outset? Will we be able to detect it, and are efforts actually being made towards this observation?
Oh, that's a very exciting question. Yes. Okay. So Hawking radiation is basically, it says that the black hole emits some sort of a very, small efficient, non-efficient radiation. By non-efficient, I mean the amount of radiation emitted over time, the fraction is very small. This particular radiation is called the Hawking radiation. Its idea is that as the black hole, gulps of matter, the entire history of the matter is lost, but then this radiation is emitted. So it's not necessarily a paradox in the sense that, because there is no one-to-one correlation between the radiation that is emitted and the matter that it has engulfed. Once the matter goes in, it loses its individuality completely. That's the idea. And the radiation that comes on, you cannot distinguish or associate it whatever the black hole has eaten up. Okay. So that's the thing. So it's not completely a paradox in that sense, but the idea is new, because not new, but kind of novel in the sense that in the very earlier times, the idea was that black holes only eat up and doesn't give up anything. But in this case, we see through Hawking radiation, it gives some trace thing back. But again, because there is no bridging from whatever it's giving up and it's eating, because that information is lost completely. So there is not necessarily a paradox. Detection is, people are definitely trying, but it's very challenging, because as I said, the amount it gives away is very, very low. And there have been some indirect ways of talking about, like, for example, if the black hole gives away matter, then it will lose some of its energy, right? So the way it should grow, it would be slightly hampered as it eats up matter. So one can trace the growth of the black holes over a large time or over a large redshift space, and see whether there is such any effects of that. And those kind of things are being done, but it's definitely challenging given the fact that the contribution of this radiation is very, very negligible. And also, finally, one thing is, it's thought about that, if the black hole radiates through Hawking radiation over a large amount of time, the black holes will evaporate. And there have been concepts of black hole evaporation and a few other things. But the problem is that, the rate of the radiation is very slow. So the amount of time you need to, see appreciable changes, it's comparable to the age of the universe. So that's the challenges. Yeah.
Aditya asks, is there any ways to detect and confirm the existence of the photon sphere, or is it only a speculation as of yet?
No, it's not a speculation at all. That's a very nice question. It's not a speculation. Basically, the image that that was taken of the the M87 black hole direct image, that was basically the photon sphere. You are looking at the photon sphere, and all the changes, all the variations in the intensity or variations with time that was observed in that particular image was exactly as you would predict from a black hole of, let's say, 6 billion solar mass and the corresponding photon sphere. So that's the proof. That image is the proof. And if you see that particular image, you will see the variations of certain regions of the disk that is moving towards you. So those are basically exactly what the theoretical simulations had predicted. So that's kind of a confirmation.
Om asks, in a graph, it was shown that the stellar black holes have higher gravitational strength than the supermassive black hole. How is this possible?
Oh, yes, this is a very fun thing. So it seems contradictory, but actually it's not, because you think about what is the closest radius that you can go to a black hole, the Schwarzschild radius, right? And what is the Schwarzschild radius? It's proportional to gm by c square. Now g is constant, c is constant. The more you increase mass, the larger is the radius. That means the further away from the center of the gravitational potential well you are, right? So the effect of the curvature becomes smaller. For stellar mass black hole, the Schwarzschild radius is also small. So you are probing very close to the center of the potential well. So thereby the effect of the gravitational field is more strongly present.
Gaurav has posted, if let's say some mass goes around the black hole rotating, and then according to relativity, its mass goes on increasing as its speed increases, so how its whole mass gets to the end or in the black hole is due to the increase in mass continuously, it would never end going around the black hole.
When you say mass increases, you basically mean the energy increases, right? I didn't get this question completely, because the energy definitely can increase at if its speed increases. But then also what also happens is that as let's say a particle is around a very highly relativistic orbit around a black hole, it emits radiation and loses energy. That also happens. So in that way, it loses of energy quite fast as well, giving away energy in terms of photons or those kind of things. So it loses energy, and slowly by losing energy, it goes into smaller and smaller orbits and finally crossing the event horizon. I hope I have answered the question.
He follows up, and how so much matter gets trapped in the black hole as it is itself of very small size compared to the mass and space it is trapping continuously.
Yeah, because it's very dense. That's a black hole, right? It's very dense. So it can trap a lot of matter in a very small space. That's by definition. That's its definition, kind of. So you can basically squeeze something, of the order of a sun in terms of in the size of 3 kilometers. So And you can make it even more dense. That's a lower limit. You can make it even more and more dense. So yeah, that's how a black hole works, because the idea is that, when you have to have a stable equilibrium, you have a complete mass within a small radius. If you want to kind of stop it, you have to have an opposing force, right? But in this case, there is nothing. So whatever matter goes in, it keeps going in, because there is nothing to oppose the infall of matter towards the, gravitational center of the gravitational well. Yeah.
And ma'am, the last question is, how can we observe photon sphere if the photons are orbiting the black hole and are not getting away?
I just wanted to show something. Yeah. These are the kind of facilities that I just mentioned. Anyway, yeah. So, yeah, that's a good question. What we see is basically, the exact, let's say, the photons that will never be able to escape and completely fall in a circle, those we won't be able to very well observe. But the photons which are at a slightly larger orbit than that, which still follows some sort of an orbit for some time and then can escape, those are the ones that we can observe.
And is it true that singularity always lies in the future light cone? Shyam, next question.
Okay. I don't remember the exact this thing, but singularity anyway is a very problematic thing. So whenever we try to even theoretically talk about how the photon orbits, null orbits will behave, we try to avoid that particular point, whether it's that particular region, whether it's a point or even a ring. Sorry if I couldn't answer your question completely. I don't often remember this.
Gaurav asks, time can reverse the effect of the force due to which all things are getting trapped in the black hole, if it will be possible. That's the question. That's what he writes. Can it be possible?
Well, the thing is, the time is something you cannot reverse, right? Time is one coordinate that moves in a positive direction. Of course, the measurements of the passage of time changes depending upon which reference frame we are, or how we are moving closer to a gravitating object or not. But yeah, it cannot be completely reversed. Hypothetically, one can imagine, but yeah, this is not a very physical possibility that we can consider. So that cannot be reversed. Time only move in a positive direction. We can slow down as also time slows. How do you slow down? Passage of time depends on your reference frame. If you want to, really slow down time as much as it happens close to the black hole, the only solution to that is you move fast. You move at a very high velocity, and then only, because there is a kind of something called the equivalence principle, which can make a parallel between the acceleration of an object and the acceleration that you, quote unquote, acceleration that you face close to a gravitating object. So one of the things that you can do to slow time, you can move fast, but the problem is if you move fast, the maximum velocity with which you can move is c. So you are limited by that, firstly. And secondly, this time that slows down, this is the slowing down of time that is, that as you observe, as an observer of a particle that is close to a black hole. The time in the frame of the particle is moving on its own, according to its own time, right? This is what you are observing. So in principle, it's looking at, to you, as the particle is taking an infinite time to cross the barrier. But for the particle, it's not.
So we are nearing the end of today's session. I am grateful to Manoneeta ma'am for accepting our invitation and being here as our guest today. I'm pretty sure that beginners and physics enthusiasts alike would have really learned and understood from this discussion. Thank you, Dimple ma'am, for attending our talk and always supporting us and encouraging us. And to you, all the participants, for joining in periodically in these discussions and making it a success every time. If you want to access previous lectures in Sarabhai Lecture Series, you may check out our YouTube channel, Physics Club NIT Surat, where we upload these recordings. And with that, I hope you had a lot of intellectual fun. And we'll see you soon in the next talk. I request ma'am and Physics Club to stay back while the others may leave the meet. Thank you, everyone.
Thank you. Thank you for this nice time.